Salam, peace be upon you. My name is Muhammad Laiq Siddiqui, the father of Holophase. Part 31, Book 9.8, Validation and Testing. How to try to break the grammar. 9.8.1, Experimental predictions, turning grammar into lab tests. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. You are stepping into a new and fundamentally honest territory in Episode 9, the generative grammar. Our journey through this episode has been a majestic climb. We have traversed the entire master tree of production, from the first sentence of phi to the closed loop of self-reference. We have uncovered the language of breathtaking elegance and scope. But now, we must perform the most vital act of any true exploration. We must test the map against the territory. A beautiful map is worthless if it leads you off a cliff. A profound language is just a story if it cannot make specific, vulnerable promises about the world we actually measure. Today, we enter Book 9.8, Validation and Testing. We begin with Part 31, Experimental Predictions, turning grammar into lab tests. This is where the rubber meets the road, where poetry meets proof. This is where we shift from saying the universe is a language to saying, if the universe is this language, then in this specific experiment, you must observe X, not Y. Our anchor image is a master bridge builder standing before a chasm, with a detailed blueprint in hand. The blueprint is beautiful, elegant equations, graceful curves. It promises a bridge that will hold. But the builder does not just admire the blueprint. She orders materials cut to precise lengths. She has engineers perform stress tests on sample beams. She builds a scale model and puts it in a wind tunnel. She makes a list of failure modes. If this joint flex is more than 3 millimeters, the design is flawed. If that cable tension exceeds a calculated limit, it will snap. The building of the bridge is a relentless series of tests of the blueprint's predictions. Today, we become those engineers for the holophase grammar. The blueprint is our understanding of phi. The chasm is the unknown. The experiments are our stress tests. And we are here to find out, does this beautiful design hold weight? Here is the practical, gritty puzzle of this part. We have developed an elaborate grammatical framework. It feels consistent and powerful. But how do we know it's not just a castle in the air, a clever intellectual game? What concrete, measurable things does it tell us about reality that we can go and check? And more importantly, what would prove it wrong? The answer is the backbone of science: falsifiable predictions. A prediction is not a vague statement like phi explains everything. It is a precise, quantitative if-then statement. If the holophase grammar, with specific parameters, is an accurate description of a particular system, then, when we perform operation A, we must observe result B with uncertainty C. The must is non-negotiable. It is the grammar's promise. Let's translate some of our key grammatical concepts into such promises. From Dispersion Relations, Book 9.3. The grammar says that in a given medium, waves obey a specific relationship between temporal frequency omega and spatial frequency k. Prediction. For sound waves in a solid rod of known material, density and Young's modulus, the measured speed of sound, which is the slope of the omega versus k line, must equal the square root of Young's modulus divided by density. Test. Strike the rod, measure the frequency of its fundamental standing wave and its length to get k, compute omega. Check the derived speed against the theoretical prediction. From Topological Production and Braiding, Book 9.2. The grammar says that identical defects with winding number can have their statistics determined by braiding. In two dimensions, this can lead to anyons, with exchange phases that are not just plus or minus 1. Prediction. In a carefully engineered two-dimensional electron gas exhibiting the fractional quantum Hall effect at a specific filling fraction, like 5/2, the quasi-particle excitations will be non-abelian anyons. If you perform a specific braiding sequence of these anyons in an interferometer, the electrical conductance will shift by discrete quantized values determined by the topological calculation, and crucially, the result of two successive braids will not simply be the sum of the individual braids, non-abelian. Test. Nanofabricate an interferometer on such a material. Use gate voltages to create, move, and braid quasiparticles. Measure conductance with extreme precision. The observed steps must match the predicted braiding group matrices. From the Dynamical Action Principle, Book 9.4. The grammar says that the path taken by a system is the one that minimizes or extremizes the action S, which is an integral over a Lagrangian built from phi and its derivatives. Prediction. For a laser pulse propagating in a nonlinear optical fiber, the shape of the pulse over time will evolve according to the nonlinear Schrödinger equation, which can be derived from an appropriate action for the light field's amplitude, a phi field. This equation predicts specific soliton solutions, pulses that propagate without spreading. Test. Launch a pulse of a specific shape and power into the fiber. Measure the output pulse shape after a known distance. It should match the soliton solution predicted by the action-derived equation, not disperse like a normal wave. From Consistency Maintenance and Topological Protection, Book 9.7. The grammar says that topological invariants are conserved. Prediction. In a superconducting ring, the magnetic flux trapped inside is quantized in units of h bar divided by 2 times the electron charge. It cannot take on any intermediate value. Test. Cool a superconducting ring in a magnetic field, then remove the field. Measure the trapped flux with a squid magnetometer. The measured flux will be a staircase function of the initial field, jumping between exact integer multiples of the flux quantum, with no stable values in between. These are not mere examples. They are the grammar's promise. Each prediction has a number attached. Each number can be compared to a measurement, and each measurement can have error bars. If the number falls outside the error bars, the promise is broken. So here is the point. The Holophase grammar is not a philosophy to be believed. It is a set of engineering specifications for reality. Its validity is not decided by its elegance, but by its ability to survive a gauntlet of pre-registered quantitative tests. We must actively try to break it. Let's explore the triunity of experimental prediction. The time echo of prediction, forecasting the future. A prediction is inherently about time. It says, if you set up conditions now, then at a future time, the instrument will read value X. The time echo is temporal anticipation. It transforms the grammar from a description of what is to a tool for saying what will be. This is the power of physics. It lets us hear the future in the present equations. A failed prediction breaks this anticipated rhythm, revealing a flaw in the temporal logic of the grammar. The space echo of prediction, mapping the unseen. Predictions often concern places we haven't looked yet. If your theory is right, then inside that neutron star, the matter should be in a superfluid state. Or, if phi is configured this way, then at an angle of 30 degrees from the beam, you should detect a particle. The space echo is spatial prophecy. It uses the grammatical relationships to chart territories beyond our immediate sight. A failed prediction is like a landmark missing from the map, showing our coordinates are wrong. The motion echo of prediction, controlling the outcome. The ultimate test of understanding is control. A prediction enables targeted intervention. If we want to create a Bose-Einstein condensate, we must cool this gas of rubidium atoms to below 170 nanokelvin and trap it magnetically. The motion echo is prescriptive power. We don't just predict what will happen, we use the prediction to make something specific happen. If our prescribed actions fail to produce the predicted outcome, our grammatical understanding of the cause and effect verbs is deficient. Now, let's locate this rigorous node on the master tree. We are at the root of Book 9.8, Validation and Testing. This node, Experimental Predictions, depends on every book that came before. We need a full grammatical framework to have something to test. It enables the honest synthesis of Book 9.9. We cannot claim to have synthesized physics in phi if we haven't first subjected the phi framework to the same brutal empirical scrutiny that physics itself endures. This branch is the quality control department of the Holophase enterprise. To see prediction in action across scales, let's light lanterns from clear test cases. A near lantern from cooking, a tested recipe. A recipe is a predictive grammatical rule for a chemical system, food. It says, if you combine exactly 250 grams of flour, 150 grams of sugar, 2 eggs, etc., and you mix them in sequence S, and you bake at 180 degrees Celsius for 25 minutes, then you will produce a vanilla sponge cake of height H and texture T. This is falsifiable. If you follow the steps and get a dense, burnt brick, the recipe, your model, is wrong or incomplete. A good cook tests recipes, adjusts variables, oven calibration, altitude, and finds the true, reliable predictive rules. A middle lantern from aerospace, simulating re-entry. Before the first space shuttle re-entered the atmosphere, engineers had a complex model, a grammar of fluid dynamics, heat transfer, and material science. They made precise predictions. At time t equals 1200 seconds, the leading edge temperature at coordinate x will be 1500 degrees Celsius. They built wind tunnels and conducted simulations, mini-experiments, to test these predictions. The safety of the crew hinged on the model's predictive accuracy. A failed prediction in the simulation would mean a redesign. The 2003 Columbia disaster, tragically, was a case where a risk, foam strike, was not correctly predicted to cause catastrophic failure, a brutal failure mode of the model. A far lantern, from cosmology. The prediction of the cosmic microwave background, CMB, spectrum. In the mid-20th century, the Big Bang model made a stunning prediction. If the universe began hot and dense, then it should be filled with a nearly uniform bath of microwave radiation left over from its early, opaque phase, with a specific black body spectrum corresponding to a temperature of about 5 degrees above absolute zero. This was a bold, numerical prediction. In 1965, Penzias and Wilson accidentally discovered this radiation. Later, the COBE satellite measured its spectrum with exquisite precision. The data points fell perfectly on the predicted blackbody curve. This was one of the most successful predictive triumphs in scientific history, turning cosmology into a hard science. It was a direct test of the grammar of the hot Big Bang. From the kitchen to the cosmos, a unifying principle. A true understanding manifests as the ability to make specific, numeric, and vulnerable predictions about the results of interventions. The credibility of the understanding is proportional to the risk of being wrong it is willing to take. What then is the specific language role of an experimental prediction? It is the grammatical sentence in the imperative mood addressed to reality. It is a command to nature. Show me this number. More formally, it is the deductive consequence of the grammatical rules, the axioms and production rules, when applied to a specific initial condition, the experimental setup. It is the output of the universal parser when fed a description of the lab apparatus. The core question this part asks about phi is, for a given concrete experimental arrangement that we can describe as an initial and boundary condition for the phi field, what specific quantitative outcomes does the Holophase grammar predict for the readings of our instruments? We are moving from the abstract how of generation to the concrete what of the next measurement. What does this predictive framework do? It forces clarity and precision, banishing vagueness. It enables rigorous testing, defining clear pass-fail conditions. It drives technological innovation, as predictions often suggest new ways to measure or control. It builds cumulative knowledge, as past tests strengthen the grammar, and failed tests pinpoint where refinement is needed. Now, stability and breakdown. The process of making and testing predictions is the stable engine of science. It holds as long as experiments are replicable and measurements are honest. It breaks down when predictions are post-dicted, made after seeing the data, are unfalsifiable, Phi explains it somehow, or are constantly amended with ad hoc excuses to avoid rejection. A healthy scientific grammar must have a clear domain of applicability and known failure modes at its boundaries. This brings us to the heart of our method, defining the falsification test. It is not enough to say a theory is falsifiable. We must specify the exact observation that would kill it. The central claim for Holophase. The entire grammatical structure, from the nature of phi to the closed loop, must yield a network of interdependent quantitative predictions across all scales of physics. The failure of a core prediction, one that arises from a fundamental grammatical rule shared by many sectors, would necessitate a fundamental revision of the holophase framework. A concrete multi-sector measurement scene, testing the topological quantum dynamical nexus in a quantum Hall interferometer. This experiment tests predictions stemming from topological production, defects as anyons, wave production, quantum interference, and dynamical grammar, the unitary evolution of the quantum state. We use a two-dimensional semiconductor heterostructure cooled to near absolute zero and placed in a strong magnetic field, tuned to the fractional quantum Hall regime at filling fraction 5/2. We nanofabricate an interferometer. A small island of the electron fluid is isolated, with two possible arms for quasiparticles to tunnel around it. 1. Prediction from topological grammar. The quasiparticles are non-abelian anyons. Their braiding statistics are described by a specific mathematical structure, the Ising topological quantum field theory. This predicts that the interference pattern, the conductance as a function of magnetic field or gate voltage, will show a characteristic even-odd effect, depending on the number of quasiparticles trapped on the central island. With an even number, interference follows one pattern. With an odd number, it follows a different, distinct pattern. 2. Prediction from wave dynamical grammar. The detailed shape of the interference oscillations and their dependence on temperature and voltage bias are predicted by the full quantum dynamical calculation incorporating the specific edge state model and the anyon braiding rules. The pass condition, validation. The measured conductance shows clear, robust interference oscillations. Most critically, when researchers use gate voltages to deliberately trap a specific countable number of quasiparticles on the island, the interference pattern jumps discretely between two distinct types of oscillation patterns, correlating perfectly with even versus odd particle number. The detailed temperature dependence of the oscillation amplitude matches the theoretical prediction from the dynamical model. This would be a home run validation, confirming that the holophase grammar sectors are working together correctly to describe a complex quantum reality. The fail condition, falsification of core concepts. Several failure modes exist. Failure of topology. No interference pattern is observed at all, or the pattern does not depend on the parity of the trapped quasiparticle number. This would suggest the quasiparticles are not non-abelian anyons, falsifying that sector of the topological production grammar for this system. Failure of unitary dynamics. The interference pattern is seen, but its detailed functional form, for example, how it decays with temperature, systematically deviates from all possible models derived from unitary phi dynamics, even after accounting for known experimental imperfections. This would suggest a fundamental flaw in how the grammar describes quantum evolution and decoherence. The even-odd effect is seen, but the magnitude of the conductance jumps implies braiding statistics that are mathematically incompatible with the other observed properties of the 5/2 state, like its electrical Hall conductance. This would mean the grammatical rules are giving contradictory predictions for different measurements of the same system, a fatal inconsistency. This multi-pronged test shows how validation is not a single checkmark, but a stress test of the entire interconnected grammatical structure. Let's cultivate a practical recognition skill. You can train your mind to spot a true, testable prediction in any claim about how the world works. Look for the if-then structure and the measurable quantity. Evaluate a business plan. A good plan says, if we invest X dollars in marketing campaign Y, targeting demographic Z, then we expect a 15% increase in sales within Q3, measurable by point-of-sale data. This is a falsifiable business prediction. If sales don't rise by approximately 15%, the model of the market is wrong. Listen to a weather forecast. It says, if the current pressure system moves as modeled, then rainfall probability for the city tomorrow afternoon is 80%. This is a probabilistic prediction based on atmospheric grammar. You can check it tomorrow. Consider a medical diagnosis. A doctor says, if the patient's symptoms are caused by bacterial infection H, then a culture test will grow colony type C, and the antibiotic A will reduce fever within 48 hours. The test and the treatment are both predictions of the diagnostic model. Whenever you hear a claim that can be rephrased as, under these specific conditions, measure that specific thing, you are in the realm of experimental prediction. You are seeing the scientific attitude. We must connect this rigorous discipline directly to our holophase journey. In the previous part, we concluded with the beautiful closed loop. That loop would be a sterile logical circle if it did not open out onto the world of empirical data. Validation is how the loop grounds itself. The phi field generates observers. Those observers devise tests of the phi grammar, and the results of those tests feed back into refining their models of phi. This is the closed loop in action, a self-correcting cycle of prediction and test. We haven't abandoned the poetry for dry numbers. We have shown that the poetry must be accountable to the numbers to be true. If you want to see the full mathematical derivations and exact equations behind these predictive models, the detailed calculations of anyone braiding matrices, the nonlinear Schrödinger soliton solutions, the quantized flux formulas, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. Let us pause at the outset of book 9.8 and feel its sobering, vital importance. This book is the guarantor of our integrity. It transforms Holophase from a potentially unfalsifiable worldview into a working scientific research program. It is our promise to you, the listener, and to the world. We will not just tell a beautiful story. We will put its claims on the line in the lab where they can be broken. In the next part of this book, we will look at the other side of the coin, failure modes and boundaries. We will preemptively ask, where do we expect our current grammatical understanding to fail? What are the edges of the map? This is not an admission of weakness, but a sign of strength and intellectual honesty. Before we end, the mandatory zoom out to hold our scope. Experimental predictions are logical consequences of the phi grammar applied to specific configurations. The numbers we predict are computed from the relationships between phi and its derivatives. We have added no new substances. One field phi, plus its infinite tower of derivative questions, plus the courage to say, this specific number must appear or we are wrong. From this commitment to testing, the generative grammar earns its right to be called a description of reality and not just a dream. As we conclude, hold the image of the bridge builder with her blueprint. The Holophase grammar is that blueprint. Every experiment we have discussed, the sonar pulse in the rod, the anyone braiding, the soliton laser pulse, the flux quantum, is a stress test, a load-bearing joint in the bridge we are building between mind and cosmos. We are not passive admirers of the design. We are the builders, the inspectors, the stress test engineers. And we will know the bridge is sound only when it carries the full weight of evidence across the chasm of the unknown. Let the testing begin. Salam and peace be upon you.